Welcome everyone to lesson 3.11 of Precalculus, which is all about secant, cosecant, and cotangent functions. So let's dive in. Secant, cosecant, and cotangent are words that may seem alien to you. And if they are, I'm sorry, I do wish that they got introduced to you before. Sometimes they get introduced in geometry, sometimes they get introduced in Algebra 2, but if this is the first time you're seeing it, it's not as bad as it seems. So let's start off with some vocab and treating these as ratios in right triangles. So we have opposite of our hypotenuse is sine, adjacent of our hypotenuse is cosine, and opposite of our adjacent is tangent. What happens if we flip those ratios, if we take the reciprocals? So instead we have hypotenuse over opposite, hypotenuse over adjacent, and then adjacent over opposite. We get the cosecant, secant, and cotangent ratios. So we're going to define cosecant as hypotenuse over opposite. We're going to define secant as hypotenuse over adjacent, and we're going to define cotangent as adjacent over hypotenuse. So, clear note, every co-function, function that starts with a co, is paired up with a non-co-function. So cosecant is paired with sine, secant is paired with cosine, and cotangent is paired with tangent. So sine and cosine aren't matched here, secant and cosecant are matched here. There's a reason why that naming convention is the way it is, and we can talk about that and discuss that later. But for now, cosecant, reciprocal of sine, so cosecant, abbreviated CSC, is the reciprocal of sine. Secant, abbreviated SEC, is the reciprocal of cosine, and cotangent, noted as COT, is the reciprocal of tangent, which also means that it can be defined as cosine over sine. So let's use these new ratios and find some values. So just like before, if we're trying to evaluate something and we have it on the circle, we're going to use our knowledge of the circle to do that. So pi over 6 is in the first quadrant. Pi over 6, it's the smallest angle, so it's across from the smallest side. Root 3, 2. Cosecant is hypotenuse over opposite. So 2 over 1. So in this case, it's 2. Interesting. Secant, this is in quadrant 2, because we're 3 pi over 4, is 1, 1, root 2. Secant is hypotenuse over adjacent, which means it's 1 over root 2, which means this is the square root of 2. Cotangent, this is in quadrant 3, so we are pi over 3 more than pi, right? Medium angles across the medium side next to the smallest side, and our hypotenuse here would be 2. Ooh, I messed up. Look at this. If you called me out on it, good for you. This one here is negative, so this would have actually been square root of 2 over negative 1, which is negative square root of 2. Ooh, look at that. Missed really messing up. So for this cotangent here, the 1 is negative and the root 3 is negative. Cotangent is adjacent over opposite. So it is negative 1 over negative root 3, so negative 1 over negative root 3, and that reduces to the positive square root of 3 over 3, and that's what we're going to use. So not too bad, especially when we have values on the circle. That makes everything better, right? What if we don't? The what ifs, right? What if we don't? Well, you have to use your calculator like you did before, but you have to be careful. So we have previously defined that this notation is sine inverse. It is not reciprocal notation like it would be with normal powers of negative 1. So when we plug this in a calculator, when we use our calculator to do this, we cannot use the inverse sine button. That is a different function. What we have to use instead is we have to convert them to sines, cosines, and or tangents. So in this case, this would be 1 over sine of pi fifths. So when I plug in my calculator, I have to do 1 divided by sine of pi divided by 5. Make sure that you're careful and that your parentheses and how you're setting it up is okay. Otherwise, what we get here is we get a value of 1.7. Essentially, 0.1, if we want to be technical. Secant, is defined as the reciprocal of cosine, so cosine of negative 1.43, and we keep the inside the same even when we take the reciprocal. So 1 divided by the cosine of negative 1.43 is 7.126. That's pretty large, especially since sine and cosine are between 1 and negative 1. These are a little bit weird. What about cotangent of pi? Well, if I do 1, so hypothetically this is equivalent to 1 over the tangent of pi, 1 divided by the tangent of pi, I get divided by 0. Why? Why do I get divided by 0? Well, remember that we can define this as cosine over sine. So what is cosine at pi? It's negative 1. Sine at pi, though, is 0, and that's where we get that divide by 0. So this does not exist, or is undefined. Either way you want to describe it is perfectly fine. So we get these values here. Interesting. So reciprocals, again, you have to be careful. We're now introducing this aspect of division by 0. So the behavior is going to be interesting. Let's start and break down each of these functions one by one, and let's look at cosecant first. So I have this beautiful sine curve. We know it. We love it, right? We're going to have a vertical asymptote everywhere that sine is 0. So I'm going to draw some vertical asymptotes every time we have sine be 0. Interesting. We're going to have a relative minimum at 1, where sine is 1, and we're going to have a relative max of negative 1, where sine is negative 1. So we're keeping these points. And if it's a relative minimum, it must go above. If it's a relative maximum, it must go below. So we get what essentially looks like, and I affectionately refer to as teeth. I know, a little bit weird, probably not the best way or metaphor there you have, but to me it kind of looks like an open mouth with teeth that are, jagged and not quite beautiful. Your dentist definitely would not approve. The domain of this would be negative infinity to positive infinity, except for angles that cause sine to be 0. By default, this we know to be whole values of pi, right? Let's look at the range. The range is the interesting part. We can see that we have two distinct y value sets. The first set is we have negative infinity to negative 1, inclusive, and then we have 1 to infinity. So we've lost everything between negative 1 and 1, which makes sense because sine is restricted to everything between negative 1 and 1. Well, what happens when you take the reciprocal of something that's between 0 and 1? What's the reciprocal of a half? It's 2. What's the reciprocal of a third? It's 3. Reciprocal of a tenth? It's 10. So everything between negative 1 and 1 is getting mapped to a value outside of it. So that's quite interesting. And because we are dealing with the reciprocal of sine, the period stays 2 pi. And in fact, we can do something cool when it comes to our key points, is we can keep our key points. We just change every single one of the zeros or the middles to undefined, to a vertical asymptote. So that is the key difference there. We can still use the same key points as sine. So we are undefined up, undefined down, undefined. So not too bad. Secant, well, not much different than cosecant, really. You're just doing it with cosine. So everywhere that cosine is 0, you have a vertical asymptote. Everywhere that cosine is 1, you have a minimum of 1. And everywhere that cosine is negative 1, you have a maximum of negative 1. And we get, again, these teeth-looking function. Now, we know that cosine is just a transformation, a translation horizontally of sine. So the secant is just a horizontal translation of cosecant. So that's why we see that same behavior of these like gapped teeth. The domain is the same idea. It's everything except for where cosine is 0. By default, this is pi over 2 plus whole values of sine. The range, just like cosecant, is negative infinity to negative 1 and then negative 1 to infinity. And the period stays 2 pi because the period of cosine is 2 pi. We can again keep the same key points. We just change everywhere that it would have been a 0 or the middle to undefined in a vertical asymptote. So not bad, really not bad. Cotangent, we get some interesting behavior. So we have a vertical asymptote everywhere where tangent or sine is 0. So every time we cross the x-axis here, by default, we get a vertical asymptote. The zeros of cotangent are where cosine is 0 or where tangent itself is undefined. So anywhere we could have an asymptote before turns into a 0. So that's a little interesting in itself. And then the reciprocal of 1 is 1. The reciprocal of negative 1 is negative 1. So we get what will eventually be a function that always decreases. So tangent is a function that always increases. Cotangent is a function that always decreases from left to right. You get this like beautiful ribbon effect when you have both functions on the same plane. So that's interesting. The points of inflection, just like tangent, are at its zeros. Its domain, like the others, is negative infinity to positive infinity, except for when tangent is 0 or essentially sine is 0, which again, for us, is by default whole values of pi. The range, just like the range of tangent, is all real numbers, negative infinity, positive infinity, and its period also mimics tangent with pi. So only tangent and cotangent have the weird periods of pi. Key points, we can steal those from tangent. We just change all of the zeros or middles to undefined and all of the undefines or vertical asymptotes to zeros or middles. So essentially, not that bad. I don't think it's that bad anyway. If you have the other ones down, these aren't bad. So let's graph them. Let's state the domain and range, or range and vertical asymptotes, which is essentially the domain, for 3 functions, one of each, right? Now, secant and cosecant, there's a strategy. You don't have to have every aspect of this function memorized in order to graph it. It helps. It 100% helps with the interpretation of the behavior and understanding what's going on. But stick with me here. Let's try secant is cosine, 3 cosine x minus 1. Let's graph this function. So by default, I know that it's going to have a middle of negative 1, and it has an amplitude of 3. So cosine starts 1, 2, 3 above, hits the middle, 3 below, 1, 2, 3, hits the middle, and then 3 above. Mirror on the other side, yes. So we get this beautiful looking cosine curve, the W. Maybe that's the reason why it's one of my favorites. Oh, it got rid of it. Let's fix that. All right, so this is beautiful. It's great. We've done this before. What's new? Let's actually now draw secant. And how we can do that is everywhere it crosses the middle where this negative 1 brought us down. So every time it's negative 1, we're going to draw vertical asymptotes, because that is where we would divide by 0. Then we know it shares the maxes and mins of the cosine function. So we end up getting what's here in green. So you can always use the graph of the reciprocal to help you graph the reciprocal. That makes sense. And that's a key strategy I've recommended for secant and cosecant. But you can, again, also use what we've learned about before, the 5 key points, and be perfectly fine with that. That's not all it wanted us to do, though. It wants us to state the range and the vertical asymptotes. So the range, we have negative infinity to 1, 2, 3, 4, negative 4, and we combine that with 2 to infinity. That's not bad. Graphically, we can see first vertical asymptote is pi over 2, and we can see that every asymptote is pi away from it, so pi times k, 4k in the integers. Not bad. Not bad at all. Let's try this cosecant function with the 5 key points. So we'll switch back to red for this one. So our 5 key points, we know that, 1, the period hasn't changed. So we know that the period is going to be 2 pi across, and we know that we went right pi over 2. So x, y, we are starting at pi over 2, and then 2 pi away from that would be 5 pi over 2. In between those two would be 3 pi over 2. In between these would be a whole pi, and then 2 pi here. Perfect. So we have our even splits, right? This is reciprocal of sine. So it's undefined, up, undefined, down, undefined. So let's go ahead and put our undefines. Easy enough. And then we said it went up, and then it went down. So up 2 plus 1 is 3, and then 1 take away 2 is negative 1. So that is our information to graph it via the 5 key points method. So vertical asymptote, vertical asymptote. Now we don't have that one, but we can always go backwards, follow the pattern backwards. So let's continue with what we've got. So at pi we have positive 1, 2, 3. 2 pi we have negative 1. So we would essentially have this pattern here, which means if we follow this up, oh, that's a negative 2. So let's fix that over here as well. Vertical asymptote, positive 3, 1, 2, 3. Vertical asymptote, negative 1. And we can finish it off here. So we get the teeth without having to rely on graphing the sine function. As far as the domain and range, we can easily see that the range is negative infinity to negative 1, negative infinity to negative 1, union, 1, 2, 3, 3 to infinity. And as far as the asymptotes go, we can see that we have the same exact asymptotes that we had before. So we get, the first one is at pi over 2, and they're every whole value of pi after that. That looks ugly. It's fine. All right. Cotangent. You really just have to go with your gut on this one. I personally would do cotangent using the 5 key points method. I wouldn't actually draw the tangent because as we can see from up here, it's not as clear cut as the others, where it's quite nice to actually use the reciprocal function to help you graph. Here I would use the 5 key points. So we have to keep everything in mind. What's going on here? We have an amplitude of 2. We have a period modifier of 2, and we are going left pi. So what is the period? The period, well, period is equal to, in this case, pi. It's not 2 pi because the default period's pi, divided by 2. So period's pi over 2. So for our key points, we have x and y. We're starting at pi, negative pi, because we went left. And then we want to end up pi over 2 after that, so that would be negative pi over 2. And this might be a little tricky to think about, and that's okay. What's in between negative pi and negative pi over 2? Well, that would be 3/4, so negative 3 pi over 4. In between these, so we have, in terms of eighths, we have 4 eighths here, so this would be 5 eighths, 6 eighths, 7 eighths, and that's how we can get that. As far as the y values go, what does tangent do? Tangent is 0, 1, undefined, -1, 0. So cotangent would be the reciprocals, undefined, 1, 0, -1, undefined. Let's place these on our graph. Oh, I forgot the amplitude. So instead of 1 and -1, it would be 2 and -2. That would have been bad. All right, so negative pi, we have an asymptote. Negative pi over 2, we have an asymptote again. In between those is 0, and in between these is +2 and -2. So this is what the first period looks like. Personally, I would prefer not to have to do this over and over and over again, but I'm going to do it without as much detail. So we have this one, and we have this one, and this is really what I want to show, is the asymptotes. So we know for the range that this is a negative infinity to positive infinity function. There's no transformations that are going to really affect that. The asymptotes, though, we can see that we have one at 0 and then 1 pi over 2 after that, and it seems to happen every half pi. So for us, we can kind of use the every half pi as a cheat code. So x is equal to half pi, or pi over 2, times k. So for every half pi, we have an asymptote. And that is it. If you have any questions, make sure you ask. Otherwise, I'll see you in the next lesson.